All right. So let's make. Oop. Let's get it. Just close Eclipse there. Oh yeah. Otherwise, it'll just upset me every single time I see it. Okay. So how did the homework go?
It was hard.
So the actual sorting part of it probably wasn't as bad as the I/O part of it. Okay, so what does that tell you? When we look at the DOS API, spread this out here. So here's our DOS API. We have the ability to read a character in. We have the ability to write a character out. We can write a string out. We can do a buffered input where we can read things in a string at a time. But everything is dealing with ASCII values as opposed to numeric data. Go ahead.
Well, I mean, bringing it in, what I had to do was just make it so that you'd enter 3 characters, so everything was a 3-character input. So it'd be 0, 0, 1 or whatever. And then what I had
so you force them into a... Okay.
And then what I would do is the first one I multiply by 100, or subtract the 28 or 48, whatever it is, to get it back to 1. And then multiply that by 100, and then add that to the second one times 10.
And I said for the assignment that they could be all positive numbers, right?
Yes.
Okay.
So I multiplied by 100, then by 10, and then just added them all together.
Okay.
So I had that in the array, and then sorted the array, and then the output was the hardest.
Gotcha.
I didn't really get that, but.
So you had some preconceived. Okay, so why did you assume it was 3 characters?
Because the highest number you could get was 255. So
0 to 255 is our range that'll fit in an 8-bit register, right? Mm-hmm. And the assignment was to fill a array. How many? What? 64? 20? 20.
Up to 20.
Yeah, up to 20 bytes.
Mm-hmm. Yeah.
So they were byte values, right? Is that what it? I mean, I didn't even read it. So.
Didn't read it.
Okay, you guys got to tell me what I assigned you.
In one of your
okay, so we had 20 byte values. So the mag, and I do remember saying that it didn't have to be signed. So positive numbers only, right? All right, so that's 0 to 255 is our range of values. So reading them in, you had them. Did you read it in as a string or did you read it in as a char?
I just did 3 different chars.
Okay, so you.
It would input one, input the other, input the next.
But you force them into 3 digits.
Yeah.
Okay, gotcha.
Well, if you did string, it'd be a lot harder to get them out of ASCII. Yeah. So rather than you just read it into a string, and then you can subtract whatever the hex value is from the ASCII.
To do the conversion one way. The going back the other way is the harder part. Mm-hmm. Because so you converted the char 3 into the int 3 by doing ASCII math, right?
Yeah.
That's effectively what you did. Okay.
And then for the 100, or for the first value entered, you multiply by 100. Second would multiply by 10. And the other one would be multiplied by whatever. But
yeah, you don't have to have 3 values to do that. What you do is you just multiply after the fact, you get the second one in, and then you add it to the previous.
How would it work if you read it in as a string? So let's say we had something like this. So we'll deal with the input first, and then we'll deal with the output, which I think is harder. But
Really? I thought that was.
Well, if you do it right, it's harder.
What is right?
Well, probably not what you did.
I divided by 100, concatenated onto a string going backwards, and then printed out the string.
You just divided by 100 once?
No, it was.
Deconstruct, yeah. But that's along the lines of what you're supposed to do, anyways. So you probably did it right. You're probably just underestimating how hard it actually was. So I heard you did your homework at a bar.
Well, I didn't do the input and output at the bar.
All right, so reading in numbers. So an interesting thing here. So we're going back to an operating system from years and years and years and years ago, and we see that this operating system seems to be very talented at reading in characters and slightly less, but fairly talented at reading in strings, right? Its version of strings. these $ terminated things, which we messed with in class quite a bit last time. But it doesn't seem to have any talent dealing with I/O with numerics. Yet, internally, doing math with numeric values is easy, right? We have all sorts of functions for doing math with them, not for actually displaying them, though. So you kind of put yourself in the mentality of somebody who wrote an operating system all those years ago, and you kind of wonder what they thought people would, what they thought people would use the operating system for when you start looking at their API. So, a lot of these things are file I/O type stuff. But if we kind of go through that, this is, so creating a file, this is all file system stuff. Opening file, reading from a file, this is going to read in ASCII values, one character at a time. So reading from a file is really no different than reading a character from standard in. Just the source you're reading it from is different. And since DOS is not POSIX, a file is differentiated from input, whereas a POSIX operating system, everything is a file. So that's why we have functions for doing that. So this is this API kind of indicates that DOS, from a visual perspective, letting the user see something, was very, very focused on characters. Didn't really consider that we might want to output numbers, mathy stuff. Well, you can output the character associated with the ASCII value 14. Or ASCII value 4, or the ASCII value 7, or the ASCII value 1 followed by a 4, that kind of stuff to get you the visual output you wanted, but you're going to have to convert your number. So if we read something in the format like this, let's say 126. So we'll read in a string that looks like 126, as opposed to you went in and you basically read in char 1, char 2, char 6, right? You read in 3 separate chars. Now, you did the conversion as you were reading them in?
So what happened was I read them all in, stored them in the registers, and then multiplied it, so basically.
So you multiplied this by 100, this by 10, this by 1, and added them all together? Well, you first converted this to its...
ASCII equivalent.
Got it. Okay. Yeah, so let's not do it that way, because that's not what the cool kids do. All right, so we're going to...
What is the cool kid way?
Well, what we're about to do here,
yeah.
which is significantly more challenging than that. But what's nice about what we're going to look at here is that it'll also work for larger numbers. So we have a string like 126 coming in, and we want to turn this into the number 126, the equivalent number 126 in decimal. So I want us to, since we're more comfortable working with decimal, we're going to try to continue to work with decimal here, even though the emulator is predisposed to hex, right? But let's force decimal because it'll make it harder. Seems like a good enough reason for me. All right, so if we want to turn the string 126 into the number 126, how do we go about that? First of all, can we do this? Can we read in this string? Yeah.
Supposedly, based on conversation 2 minutes ago.
Yeah. Well, and we have an API, right? Where's our buffered input? This guy. This guy should be able to read something into a buffer. Do we have actually reading in a string, or is buffered input the only?
There's nothing string based.
All right. So this returns a buffer filled with user input. So we have. We load into AH0A. This is going to be buffered input. Then we load into DS. Well, we load into DX, the offset of a variable which is our buffer. Make sense? So if we're going to keep it relatively simple for this, what's the biggest number that we can have for this assignment? 255. So 3 digits. So how big does our buffer need to be? So really probably 4 because we need the string termination, right? So, but we don't need to accommodate a humongous buffer. But we certainly can go with a larger buffer to handle larger numbers. So what's the biggest number that we would be able to represent in 8086 without getting super creative with registers? Because technically you just take a whole bunch of 16-bit registers and just start saying, well, these 4 registers represent the first 16 bits, followed by the next 16 bits, followed by the next 16 bits, followed by the next 69. You got a 64-bit number. So you could technically pull it off. But so realistically speaking, our registers are 16-bit registers. So our range of values is 16-bit numbers, so 0 to 65,535. Or if we want to do sign, negative 32,768 to positive 32,767, but that's our range, right? Okay, so 65,760, 765, right? 0 to 65,000, 65,535. So we have 5 digits is the maximum length of a number we can store in a 16-bit register. Sound reasonable? All right. So let's go in here. We'll deal with our, I'm going to delete a lot of this. So we're going to call this guy buffer. This guy is going to be a data byte. And it's going to be, oh, what did I click?
Everything.
Eclipse is uninstalling. What did I say, 5? So we'll have 6 buckets. Fair enough. Okay. And that should be good enough for us right now. And then let's go ahead and we'll take message out of here for a second. All right, so we want to look at this, we want to load into AH0A. So let's just kill off all of this. Throw a return there at the end. Read char, write char. Let's leave those in existence for right now. So let's do read string. This guy will be a proc. P read string. We'll throw our return at the bottom of that guy. Let's indent this return. Okay. So we need to move into AH. So move AH 0A, and that's a hex value, right? Or we can do the 0 by 0A. That looks cooler, doesn't it? That we decided that last time too? It just looks cooler. All right, so we'll move into AH, that system call, the guy we want to do here. By the way, old Alex, did you watch any of the videos? Oh, you're going to be so lost. You're already lost, aren't you? This is good, just gone. Yeah, just nothing.
See, when he's watching the video and they don't have Vietnamese subtitles, there's only so much you can do.
That would be actually a pretty funny joke to see if, well, I say joke, but there's probably software that will go through and translate your an English-speaking video into subtitles in other languages, at least close, right? I start putting videos up with Vietnamese subtitles.
That'd be great.
Well, maybe it would be better if the videos converted my English, well, English-esque into Vietnamese, not subtitles, but got the English as subtitles and dubbed over Vietnamese. Be like those, the Kung Fu movies, right? Something like that? I think so. All right, so we'll move into AH, the read into a buffer guy. And then we need to move into DX, the offset of our buffer. Okay? So we're going to go ahead and we'll move into, where am I here? DX. Now, how do well, here, I already said it out loud, so we'll just do it. So we'll say offset buff. What value does that return for me? Not Curcio, since we talked about this much today. Memory address of the buff. Okay.
16 byte.
The who? Starting address. So the offset of, so the base address of buff relative to the starting address of our data segment, which is stored in DS, right? So that's what this guy says right here, is DS should hold the base address of our whole data segment. Okay, and our whole data segment is like a giant array. Let me go ahead and put that in here because it's kind of important for us, even though I covered it earlier in Curcio's class.
Like he was paying attention anyways.
He was.
I was answering questions.
See how defensive he got so quickly?
No.
How did wrestling practice go?
So,
Did you didn't was it play well, wrestle well, fight well? What do they call it?
it's wrestling. You didn't wrestle.
You didn't wrestle well.
No, it has nothing to do with that. It's just like,
It was hard practice.
yeah, like this morning we had to do like 500 sit-ups, and then at night we had to do 200. And then in the beginning of practice, and then
So you would in one sitting do 500 sit-ups?
and then at beginning of practice we did 200, and then at the end we did 100.
So you've done 800 sit-ups today.
Yes.
It is a chore for me to get out of bed in the morning.
And then
once.
we did.
Well, yeah, I mean, I have a whole technique. Okay, I got shimmy towards the end of the bed, and I lift my legs up, and then fling them forward, and that just drags everything up with it. I'm not kidding. Then I have to sit there for about 10 seconds because if I get up too quick, I'll pass out. That happened one time. That's why I sit down. So I want you to imagine. So it's hardwood floor. I'm in the kitchen. I got up to get a drink. This was, I don't know, 7 years ago or something like that. So lights out, 370 pounds, just dead weight on our hardwood floor. My neighbors came over. They heard it through the walls.
Did you hurt yourself? Or did you just
No, I couldn't even because I had a glass in my hand.
Oh wow.
Glass shattered, not a mark on me. I had I kind of bumped my arm, or basically I had a small bruise on my arm. It could have ended badly. Yeah, so now my wife makes me, I have to sit there for 15 seconds and actually count.
Why don't you do some stretches or some yoga exercises or something while you're waiting?
I do. I pop my my back in. I twist to the left to get my sacroiliac joint readjusted. It's a problem.
He's one of those people that when you're moving stuff, right? You have to lift with. You don't use your legs at all. Use your back with a swift jerking motion.
That's true.
Twisting jerking motion.
I'm going to my my shaman chiropractor this tomorrow.
Yeah.
Oh yeah, you guys, have you seen the? Did I tell you about the machine this guy uses?
Is it the one that pulls you
Check this out.
Oh man, this is gonna be interesting.
This thing.
in
It looks like a James Bond torture device.
Why is there a needle thing pointed?
He puts that.
That's the laser.
He puts that right here,
Why?
because it's awesome. Yeah, look at this. Time to go in.
Why?
It's actually kind of amazing how it works. So this is barely touching your skin, but it doesn't do anything to you. It's all It's all a sound wave. So this whole thing puts a sound wave in. The idea is it adjusts your atlas, your very top bone, and your cervical vertebrae up the top. So the idea is that you put your head on straight, because if your head's not quite on straight, then you naturally adjust your body to get your eye level. And then so when he gets your head on straight, then everything else kind of fixes itself. It's kind of it's almost like magic. I'll go in and
Shaman.
kind of bad pain, and this guy basically won't touch me. I just did the procedure to you, basically in terms of what you'll feel, even though it looks scary. It doesn't do anything. And all of a sudden you feel this big rush of blood because, I don't know, whatever once it realigns, then all of a sudden the tension's gone, and then all of a sudden
All right.
and then you're good for 2 months.
And then you burn the witch.
And there's an offering. I mean, that goes without saying.
You don't burn the witch. You throw them in the water, and if they drown,
They float. Then we burn them.
Then we burn them.
Yeah, what is this? Is this your first rodeo?
Sorry.
We have to see if
Forgot
we
the
weigh more than
procedure.
a duck.
By the way,
And then-
you should ask him. You should ask your shaman if he has totems.
His totems. I'll do that tomorrow, and I'll video record his answer. All right. So we're going to connect a few dots here. So down here, let's go here. Well, because I'm going to do a little bit more in here for it. All right, so we have a couple of registers. We have DS. Now, when we load our program, what value does DS hold?
700.
Oh, okay. In our emulator, it does actually hold a specific value, but what's the meaning of the value it holds? That's what I'm more getting at.
Where the data segment starts.
So the offset, based on what the very beginning memory address that this guy's inserted itself into of where the data segment is, right? So by this example, it would be 100. All right. So our data segment looks like a big old array. All right. So this is memory address 100. This would be memory address 101, 102, 103. Now, if we have a couple of values in our segment here, so actually let's use our example. So we have our dot data here, and let me left justify this, and we do what do I have? Buff db4 6. What do I have? 6.
Yeah.
All right. So buff db6. So that's but Freudian. All right. Was it?
Yeah.
Oh. Thanks for having my back, you churro stealer.
Cool.
Ay. Oh, there we go. Okay. So when we do our buff db6, the perception here would be that since this is the very first variable that we're defining inside of our data segment, it's going to be contained within the very first portion of our data segment's memory. Okay, so I'm going to need 6 bytes for this guy. I didn't actually put values in there, but let's just, we'll put some X's in here. Okay. All right, so this is buff, and when we read through the data segment, when the guy's being assembled here, it's going to go through and grab all the variables in here and assign memory addresses to them relative to DS, the address that's stored inside of DS, which is the base address of our data segment. Okay. Similarly, what's stored in CS? Those two registers. If DS is the base address of our data segment, what's stored in CS? Okay, so the base address of our code segment, right? So we have a data segment, we have a code segment. So just for the sake of argument here, let me go ahead and just create another variable. Call this guy Churro for no great reason, I guess. And I guess I should have made it maybe like a double word if I'm gonna have to represent the number of carbs in it. All right, so we'll set this guy equal to 15 for no good reason, just to have a value in there. All right, so this is going to be another data byte, and so that guy will live right here. So there's our 15. It would actually be stored in hex, but whatever. Okay, so these are the currently these guys right here are the empty contents of our buffer that we're about to use. All right, so if after we load the data segment, if we were to look at the actual memory associated with our data segment, it would look like this. That is, buff, the offset of buff would be 100. So that's the base address of buff relative to the beginning of DS. and it would go all the way to here. And then if I did the offset of churro, it would return 106, which is its base address relative to DS, the beginning of our data segment. That make sense? So all these guys are in contiguous memory. They technically wouldn't have to be, since offset, they would have to be contiguous memory in and of themselves, but not necessarily relative to each other, since offset gives us those values. But it would be in their best interest to do this as contiguous memory to get the most use out of their data segment. All right, so we have two variables here. One of them is housed in those buckets, and then the next one is housed in this bucket. That makes sense? So when I call offset of buff, it'll give me 100. When I call offset of churro, it would give me 106 in this example. All right, so this is what our data segment looks like. So let's go back in here. So I'm going to read in a string. So I'm going to move into AH, the system call for reading in a string. Reading in, well, as Haxton keeps saying, there are no strings in here. We're reading in data. We're just going to happen to read the data in as a $ terminated string. All right, which could get interesting here. All right, so now we'll move into DX, the base address of our buffer, what the container we're going to read this into, and just tell it to start going. Make sense? Okay. And then we're going to return, so this is our read string. And let's do this. So we'll go ahead and we'll do call read string, which is going to call this guy. It'll move that guy in there, and then we'll read from buff. And then do we have a write string? Well, we'll write that in a second. Let me save this. Emulate. Okay. Let's see. Let me just run it to the end.
Uh-oh. Yeah. Here we go.
should I pause? Hold on. Let's pause the recording for a moment.
Stupid.
And we're back.
It's gonna break.
Small hiccup on the internet.
Don't know what happened there.
Yeah, that seems kind of useless, those function key things.
Seems very cliche.
Now what are we going to do?
Like if you have a music app open, like I want to keep it so that the things would be there even if I changed applications though. Like that would like annoy me. So I could like change my music without having a tab to it. And then, oh yeah, now let's use that button.
Yeah.
Like that just seems...
I would probably be relatively okay if it didn't have speakers.
But you have to use it anyway.
Well, I do watch YouTube videos sometimes, I suppose, but I don't listen to music. As long as it has a headphone jack. Okay, so let's...
Oh.
Don't
Wow.
even get me
Apparently
started.
they were interviewing people about like, do you actually use the headphone
Yeah,
jack?
one of my students earlier was mentioning that.
Is at least funny.
Oh, hold on, I reload, run. Program has returned control to the operating system. Okay.
You never had it do the thing.
Who?
You never did the 28 at 21.
Oh, the N21H. Thank you.
Yeah.
I was testing. You guys all failed. Every one of you. So while I'm at it, N21H. What does this line here do, Tim?
That tells the
Green Tim, not smart Tim.
No,
Oh, you redid it here again.
What's that line do?
is it?
It's a lot brighter. It might be the same color, but is it the same color? You were bluish before?
It's like turquoise-ish green. Oh, it's good.
Yeah. What you're really saying is it kind of looks like an Oompa Loompa.
No.
Oh my god!
He's trying to get.
And we're back.
Damn it.
All right. So what does this line do?
Interrupt.
And do what? What does 21H do specifically?
Is the amount of time the interrupt lasts?
No. Oh, so here we'll start off with an easier one. Why am I interrupting? What's the purpose of this interrupt?
line?
You got this.
How do you not Tim? Come on.
IO.
Is that who?
IO.
Well, yeah, that's fair enough. That's fair enough. Yeah. All right. So, so tell me more about how I was accomplished through this. It's like, you're lucky you got that out of me.
Grasp it here.
Okay, so this comes back to operating systems, and so when these are the instructions that the CPU is effectively eating, right? The CPU is going to do this guy, and he's gonna do this, and let's say we might have 50 instructions we can do in a single CPU cycle or something. Well, we only have 2 before we've done everything we can do until we now need to turn things over to the operating system. So when we interrupt, we're interrupting the CPU so that a context switch can occur, right? So that the operating system can say, okay, this process is cooked as long as it can currently cook on the CPU. Get him out of there so we can put this next process, maybe it's Microsoft Word or whatever the next program that's in line for the CPU, we can get him onto the CPU and get him cooking while I/O does its thing. Because who knows how long it's going to take us to type crap in, right? So why should we sit there and pause the CPU? Because one of the jobs of the operating system is to keep the CPU as busy as close to 100% of the time as possible. So this guy specifically says interrupt the CPU and call the DOS operating system. The DOS operating system then specifically goes and looks in AH, the 8086 architecture would know to look in AH. Newer architecture would look in the instruction sets are larger, so we'd look at AX. But this guy will look in AH and say, what is it that you want to do? I want to do that. Well, what is that? That is this guy, which is the system call for DOS for doing buffered input. Okay, so that's what I want to do. Then here's my parameter. So we're going to put parameter into DX. Why is it in DX? Because that's what the API for DOS said to do. It said put a address relative to DS, the base address of our data segment, into DX for the buffer, the guy we're actually going to read in. Okay, now look at the information related to our buffer here. So format of DOS input buffer. So we've created this buffer as a 6-character thing, expecting it to act like expecting it to act like a string. Bucket 0, so the base address of our buffer, holds the maximum characters that our buffer can hold. Bucket 1 holds the number of characters from last input, which may be recalled, or number of characters actually read. Excluding CR, so that excludes the carriage return itself, so that won't count as a character. That's the thing that ends the input. All right, so this is what's the maximum length. This is how many characters were actually read. That makes sense? And then the following n things are the actual characters read in. So if we read in 6 characters, or in our case 5 characters was the maximum length of our number before we press enter. So 65,532, something like that. Then we press enter. This guy would be a 5. That's the maximum number of things we can read in. This would be a 5. The things actually read in. And then the next 5 buckets would be 6, 5, 65,535, 532, whatever I said I entered in. Does that make sense? That's what that guy looks like. Okay. So question is, if I'm going to create this this buffer, right now we just did it as a generic data byte. How do I actually build a buffer that has the maximum characters that can be held in here? I need to build my variable with a value in mind. I have created it to be 6 buckets, right? That's in my head. We were kind of creating this guy as a placeholder for what we believed was going to be a string. And we're going to turn it into a string. Okay? But it's not going to get read in as a string. It's going to get read in as a collection of values. It will be ASCII values, so it will be as if it were a string. But it will not be $ terminated. Instead, how do we know the length? We know the length of it because the second element of buff will tell us how many things were actually read in. Make sense? So buff is going to be a data byte. And inside that data byte, we want to have our maximum length of this guy, right? So that's 5, followed by question mark. Oh, I thought I did a weird symbol just because this guy was hovering over there. That was like an alien. I think it was semicolon. All right, so followed by
Duplicate thing of 10 or however many.
So for us, it's 5,
Yeah.
right? And what are we going to have in there? What are we duping?
Empty care space.
So could it just be question marks?
I think so.
Yeah, so I mean, literally, it could be.
We're gonna have a question comma, right?
Yeah, it's question mark, and then space
Right.
dupe
You
6.
deleted the other question, so don't you need 3 things? So don't you need 5 comma question mark comma? Is that
I
again?
don't think so. It's not 3
Oh, yeah,
parameters.
yeah.
These
Right,
are just
right,
these are
right,
just
yes,
the buckets
yes,
of the
yeah,
of the
yeah,
buffer.
You're right. You're right.
So bucket 0 is the maximum, total maximum. Then all the rest of the buckets, 6 of them. So bucket 1 is a placeholder for the function to let us know how many characters it actually read in last, right? And
Well,
then
isn't it's duplicating 6. It's going to fill 6 in those, right? I thought the leading number was how many buckets you had.
is it? Is it? So it's this guy. It's 6 dupe question mark.
I think so.
That all right? Fine. We'll find out soon enough, I suppose. All right. So we'll define a data byte. Bucket 0 will be our 5, and then the rest of the buckets will be 6 question marks, filling out our starting point for our buffer. That makes sense. So this 6 or this 5 here represents the maximum number of characters we're going to read in, that we're able to read in with a system call. That's following this guy right here. Offset 0 of our buffer is 1 byte in size, so that means the maximum length is what? What's the maximum length that this function can read in? Maximum length of somebody who hasn't really answered yet today. So because this first parameter here is the maximum characters the buffer can hold, and its size is 1 byte. What's the maximum number of characters that our buffer is capable, or that this system call for reading into a buffer can read in? It only depends on the thing that I have highlighted.
So the byte size, it'd be 16.
No, it wouldn't be 16. It wouldn't be
255.
255. Well, 256, but yeah, so 256 characters would be the biggest we can put in there. Although, that's actually an interesting question. 255 would be the largest value we can put in, so it probably is 255. I think you're right. Because it's not going to zero index it. We just can't say a byte-sized value larger than 255.
Wouldn't you be able, would it zero it?
I don't think so, because you're not using it as an index. You're just saying here's the most number of characters that I can hold. It's 255 unless it treats it as an offset from 0, I guess. But I suppose at the end of the day we're off 1.
Yeah.
It's either 255 or 256. I think it's 255. I think you're right. Okay.
Because you could technically have a buffer with 0 items in it. So you could say the maximum characters is 0. It wouldn't put 1. You could have technically an empty.
Okay. So it would be either empty up to 255 total characters. Yeah. I'm not sure why would you ever have a buffer with.
I don't know why you would, but I think.
Unless you were literally building something to manipulate memory. Like you just needed a starting spot to just start walking through memory and just overwriting crap. All right. So the reason since this value is 1 byte in size, the biggest thing it can hold is 8 bits of data. And unsigned, it wouldn't make sense to have a negative buffer size, right? So that first thing is going to be the number of, can have a maximum value of 255, which is an unsigned, the maximum value of an unsigned byte, 0 to 255. Make sense? That's 8 ones. All right. Then, second bucket, this guy's going to have a value in it after we've read crap in. So he's going to give us a number that's going to be something less than or equal to this number. Right? How many things were actually read in until we hit a carriage return? Because that's what it's looking for, is the carriage return. And then we'll actually get our crap. So starting at offset 2 is when we actually start getting into the data that was actually read in. So we have to be aware, similar to having to be aware of what was at the top of the stack when we do a function call. Here we have to be aware that the first 2 values of our buffer have meaning to what's in the buffer, not the data of the buffer itself. All right, so that's kind of given information.
Wait, isn't the question mark going to cause issues then in actual code? Because technically you're not resetting anything, so you could theoretically have, well, I guess if we're doing based off of...
I don't think it should cause a problem. It might be that you don't need this. Well, you definitely don't need it. I could just do comma, question mark, comma, question mark, comma, question mark.
Right. So what I'm saying is that you're not going to overwrite that block of data, so it theoretically could be, there could be a string concatenation symbol before you want it. I don't think that would ever be an issue.
Yeah, but we're not, the thing is, a buffer is no different than any other variable in 8086 assembler.
Right.
So that's why it has these like special characteristics. We're like, okay, bucket 0 is going to mean this, bucket 1 is going to mean this, because I'm kind of just using space inside of our data segment, just like any other variable, to pull this off.
Sure, I was just saying, because you're not wiping out that 6 bucket array or whatever you're doing there, like you could technically have questionable data in there, and if one of that data was the character or the $, it might concatenate early.
Well, what do you mean I'm not wiping it out? So
The
what?
question mark doesn't actually put it to zeros or anything. It just, whatever was there, you now own, but it could be whatever was there before.
Yeah. But if this guy is nothingness, then I know I haven't read anything in.
Right, but with our emulator, it's going to be whatever was there before. It's not nothingness.
I understand what you're saying. So we'll see what it comes in. So you're saying that maybe we should default it to 0.
Right.
Saying we have not read any values in, so don't expect anything to be after this. It's probably not bad advice.
Or if you want, I guess the other issue could be is that if you're going to do like a 5-length strength or something, or 5-length string, and then you're going to concatenate onto the 6 bucket your $, then you could and you only use 3 of those buckets, you have 3 that or 2 that are questionable as well.
Yeah, I think that's reasonable. What you're saying. So let's make this a 0. Let's go ahead and build this
But
and just.
That's going to set it so that 0 characters can be input, right?
No, 5 can be inputted. 0 have been inputted on the last read,
Okay.
which we haven't had a read yet. And then here's our landing zone for our up to this many of those guys.
Right.
So let's just walk it single step. So now we should have vars. So here is our.
If you click on it, if you click on buff, it'll highlight it in there.
I'll highlight it where?
You can click on the elements right too. If you go to elements and change it to 6 or whatever.
Oh, okay. Yeah. So here's our. Actually, we have 7, right?
I have 71.
Oh,
It doesn't actually let you have 0. in
yeah.
there.
So it looks like it did 0 them all out anyways, except this first 0 we explicitly set as a 0. So probably was smart, but not necessarily.
They were 0 to begin with, and you just didn't put any.
Correct.
Yeah.
Why is what?
Okay, is that after you entered them in then?
Well, this is after just this one line right here. That's all that's executed at this point.
Why is it 5? Okay, so 505 should be the first 3.
No, because
Who?
you're doing the duplicate.
This is the maximum. This is the maximum number of characters that can be read in. This is the number of characters on the last read.
Okay.
And these should be the actual characters.
Okay.
How many? This many. All right, so let's step. All right, so let's do 113. Press enter. All right, so we just entered in 3 values. So now it should be 5, 3, and then 113 should be the next 3 things because we haven't used up the whole space. So there's our 5. There's our 3. Then we have 31, 31, 33. Somebody tell me why it's not 113. Somebody who hasn't really talked yet today. Based on some of the email questions I got for this assignment, some people are getting left behind. So we need to be more inclusive here. Is it wrong or did it work right? It worked right. So I'll give you that as given information. This worked right. So I expected it to read in 113, but it instead read in 31, 31, 33. What are those? Let's take a nap.
Sounds good.
ASCII values.
ASCII values. So those are the ASCII values, the ASCII mappings of 1, then 1, then 3. All right? So if you look that up on the ASCII table, that's what those guys are. Don't we have an ASCII table in here?
Yeah.
Click on it. Click on the main one.
Who?
The one that's back behind everything.
So
It says
do,
ASCII code to register code.
No.
do I close this?
No.
Can I close this? Do I move this?
No, sure,
You don't have to.
go for it.
So
Just
sh-
go up to ASCII codes.
No, not
I could click back here.
No, the
Yeah.
windows.
No.
Go straight
Yeah.
up. Straight up.
Yeah.
Straight up.
Yeah, click.
Click.
Up.
Oh, ASCII codes.
ASCII codes. And then click on it, and it changes to hex.
So where's my 31? There, 31 is 1, 1, and then 33 was 3.
ASCII table.
Make sense? All right. So it appears that we read the stuff in correctly. So there's our 5, there's our 3, and there's our 3 values with the last, the very last value being nothing. What's 0D?
Is that
We dealt with that last class. That's the carriage return. Yep. So it did read in the carriage return. The carriage return was read into the buffer, but this guy right here says, here's how many characters we read in, not including the carriage return.
So, what do you want to see the carriage? So you're gonna overwrite the last bucket with the dollar sign then, or no?
Well,
If you want to,
if we want to get into a string, we're going to have to do something like that. But for right now, let's get it moved into the values that are meaningful to us. Let's get moved into something else. But what this does tell us is since it is reading in the carriage return is not counted in the 3, in how many characters were read in, but it is taking up buffer space. That means if we want to really be able to house 5 things, we need to have 1 more bucket in our buffer in order to pull this off. So I got to go back to our code here. So this is actually going to be a 6, and that's going to be a 6 to give us the enough real estate for 65,535 carriage return, even though we know that carriage return is never going to be counted in this guy. That make sense? Okay. So now, that's reading a string in, and when we're done, it's going to read that string into our buffer here. We'll leave it like this. We can be a little more robust with this if we want. So now what we want to do is we want to write a string from a buffer. So we'll always load into in our example here, we'll load into buffer the string we want to write. Well, how do we write a string? here. DOS interrupts. Where are we at? 9, right? 9. Write string to standard out. So we're going to load into AH9. Then we're going to load into DX, the offset of our $ terminated string. We have a problem. So let's go here. We're going to write this function real quick. So we're going to call this guy write string. Proc. Go ahead and put my return in here. And we're going to move into AH 9H. Actually, I just move in 9, doesn't really matter. Then it wants me to go what? DX, right? So move into DX, the offset of buff. And then we do our interrupt, int 21H. Okay, so after we read a string, we should then be able to call write string. And we want this guy to read in something and then spit it back out. This is effectively an echo value, right?
Work though.
Huh?
That shouldn't work.
You're right.
Oh.
Yeah.
Okay.
All right. So we'll go ahead and run. So we'll do 113, press enter. Can I close this? Did it stop me? All right. So byte 24H not found after 2,000 bytes. So we go up here and ASCII codes, click on it, and what was it, 21? 24H, okay, yeah, this guy. $ wasn't found. So it looked for 2,000 bytes for the end of that string. Never found it. But I just read in the buffer. It wasn't a $ terminated string, but it was a buffer. So what we want to do is we need to manipulate that buffer to make it look like a string. Make sense? All right, so what we're going to do is let's take about a 10-minute break, but we're going to come back in teams. Let's see, who are my teams going to be? You like this? You like this team?
We'll do the 2 versus everyone else.
No, we got to get some experience here. So let's do. Let's see, who would be good teammates? Who thinks they really are struggling with this stuff? You? Okay, you're with Hacks then. All right, just you two, because I want to watch that. That should be funny.
Alex?
Trust me, he's actually a good guy. He's just a big mouth. Yeah. All right. So then, who else? Well, Alex. We need to put Alex with somebody who knows what the heck they're doing. So let's do Alex and Tim. I'm debating. All right. Yeah. Let's do. I'm going to do Alex with Tim because I think Tim is pretty good at teaching this stuff. And he stays on task when these other guys start fluffing around. Okay, and then you 3 on a team. Sound good?
Uh-huh.
All right, so go take a 10-minute break.
Is that all on recording?
Is which part?
Oh yeah. Descriptions.
Yeah. Oh, was any of it bad?
No.
I mean, all the people that were idiots, I said you're an idiot. And all the non-idiots, I said you're not an idiot.
I don't see a problem.
It's not slander.
All right.